Hi, everybody. Welcome to the third presentation in our Databricks lecture series. I'm really glad that you can all join us tonight. I'm Drew Pollan. I'm the academic director of the MIDS program here at the iSchool. And I'm really pleased to introduce Denny Lee from Databricks. And Denny will be leading our discussion today about bringing software engineering practices to data and to AI. So Denny is a developer advocate at Databricks. He is a hands-on distributed systems and data sciences engineer with extensive experience developing internet scale infrastructure, data platforms, and predictive analytics systems for both on-premise and cloud environments. He also has a master's in biomedical informatics from Oregon Health and Sciences University and has architected and implemented powerful data solutions for enterprise healthcare customers. His current technical focus includes distributed systems, Apache Spark, deep learning, machine learning, and genomics. I also have to say that Denny was key in bringing Databricks to support our machine learning at scale course. So a special thanks for your work there, Denny. Thank you so much for joining us today.
Hey, Drew.
Oh, yeah, go ahead. I just want to say, before we get started, I just want to let everybody in the audience know that we're going to set aside about 10 minutes or so at the end of the presentation for questions. So please do feel free to post questions either in the Q&A panel, you can see the Q&A button at the bottom, or even in the chat, and then we'll make sure to return to them at the end of the session. So Denny, thanks.
Hey, thanks a lot, Drew. Appreciate you taking the time. I'm glad. Thank you very much for the invite, and thank you for everybody who is joining for taking the time to listen to about Bernie Sanders chilling. Oh wait, no, sorry. Bring software engineering practices to data and AI. Okay, so I'll skip the slide, most of it, but since Drew already did the introduction, but I did want to provide a little context that the way this particular this particular lecture is about, is sort of about the last 15 years. And you'll actually sort of see it from my own history here, where I first actually started at Microsoft with the SQL Server team and how that progressed into big data. And so a lot of it, for a lot of you folks who you may not be familiar with the database past, that's okay. You don't have to do that retrospective per se. But there are some key learnings from the past that we want to apply. And at the same time, there's a lot of things that we're doing right now that are significantly better than we've done in the past. So I'm going to give you all that little bit of retrospective, basically. Okay. And so just in case, by the way, if you are interested in Spark itself, by the way, I happen to be the co-author of the book, Learning Spark, the second edition. My co-authors, Jules, Brooke, TD, and myself. If you go to this particular link here, and we'll send it to you right after as well, you get to download the ebook for free. Okay, so just go download it. It has lots of good stuff about Apache Spark. We also include stuff on Delta Lake, MLflow, and Koalas. Okay, all right. One little spiel about Databricks. Don't worry, this is it for the marketing slide. We are the unified data analytics platform for accelerating machine learning, data engineering, data science, and business analytics. We have thousands of customers and partners worldwide. Key thing that you care about, obviously, is that we're the original creators of the popular data and machine learning open source projects, including Apache Spark, Delta Lake, MLflow, and Koalas. Okay, there we go. Now we're done. So this particular lecture here is actually a sort of a muddled down version of this upcoming full course called Bring Software Engineering Practices to Data and AI. It's broken into 4 particular courses with multiple modules in each one on reliable data infrastructure fundamentals, the one on complexities of distributed systems, data engineering practices, and machine learning best practices. So just want to call that out, that if you want to dive deeper into the stuff and have a discussion, the Coursera course will be coming out in late February, early March timeframe. Okay. So for this one, we're going to focus more on the reliable data infrastructure fundamentals because it's sort of the baseline for where we're sort of going. And then the first question almost everybody going to ask, which is valid, is what does data reliability have anything to do with software engineering practices? Okay, because you're going like, wait, you're saying software engineering practices to data and AI. Why do you start off with data reliability? Okay, so the reason we start with that is because we're really talking about the state of data, and this is not a marketing moniker. Actually, it's a context of saying understanding the state of your data is more than just storing it. It's actually understanding what's the meaning behind it. Is there lineage? Is there additional metadata? Is there configurations? So there's all sorts of things that are associated with the state of your data, and you actually want to be able to explain that state. And so I use a relatively simple examples like, well, what's the state of your code, right? And these are just simple examples, so we can go on and have a deeper discussion on each concept. But for example, when this is just using GitHub as an example, you're using source control to track which versions you have of your code, allowing multiple people to read and write that code, roll back to previous versions. I've done that a million times because of all the mistakes I've made, and explain comments and explain or comment why you've done this, and getting feedback of why you make the changes for the code. All right, so that's the context of saying state of your code. Well, then how do you do this for your data, right? That's the real question here, right? And so what you'll realize as we talk about this a little bit is that it's actually not that easy to do this for data. And so now we're going to do the retrospective part. Let's go back about 15 years when we called the data engineering lifecycle the database engineering lifecycle. So for many of you who are attending this, you may scoff at the idea like, wait, database engineering? What are you talking about? So during my time when I was building these large database systems for Bing, and then I joined SQL Server team, for example, that's what we did. We relied on databases to hold all of our information. It was the key thing to hold all state. So that way our applications could be running, services that we were creating. At the time, we didn't call them services. They were just products, right? And we were also suffering from this awesome concept where basically, well, since you needed a database, most business analysts were saying, okay, well, Excel, that's perfect. That's my database. Okay. And by the way, I could probably redo this particular moniker to not just Excel is not a database, also Access is not a database. Yes, it is a database, but no, it's not a database. Okay. And it's not here just for jokes. It is amazing, even how today there are many businesses that the entire basis of operation is saved in an Excel spreadsheet. And so all the business logic, all the functions, what's stored. Now, obviously, Excel only holds 65,000 rows, but that's okay. You just create multiple Excel spreadsheets, right? And so the entire business operates on this one person or very few people that are able to interpret what is inside that Excel spreadsheet, and then they make decisions based off of that information. And that's actually common even today. Now, it's a lot less common than before, but it's even common today. So in the past, this was actually pretty normal. Okay. And so what this context is really leads into this idea of the monolithic approach to data. So don't worry, I'm not talking about Excel as that, but the idea is that there's one place that holds all the data. Hence the reason I use that Excel example. The idea is that the business analysts use Excel to hold all that information. And so the monolithic approach to data, when it especially comes to things like databases, all right, it's this idea that, okay, we have a central point database, all applications and clients would basically talk to this one database, right? It's the central point of failure, all data state version controls inside that one database, all that business logic is pushed in the database for faster performance. So if you look at databases and you dive into how they're built, like for example, I'll create not just the schema and the indexes for the database, but for the tables, excuse me, but I'm also going to go ahead and create stored procedures. And I'm also going to go ahead and create stored functions. And because I create those stored procedures and functions, we can compile them right next to the database. So that way they can query the data significantly faster because they've already compiled with the statistics that are there. The problem with that approach, of course, is then now everything, your entire business is tied to that database. Okay. And so that's not the funnest thing to do. Okay. And because then if I was to break it down in terms of just these 4 simple examples that I use for a la GitHub, I was like, well, how do you track which versions of data or of the code that you have concerning the state of your data, right? So if you're thinking about like, okay, well, how do I track versions? First, I talk about the code that I use to process and also create the schema for the tables and the store procedures. Well, that one I can probably do okay because I create SQL files and version control those. But then how do I version control the data? Well, that's done because I've done full or incremental or change backups and or change history tables. The former, the full incremental change backups, is a very operational heavy process where basically every night or some period we would process them. And yes, I come from the age where we would process them and save them in tape backups. Okay, we didn't have Amazon Glacier at the time. All right, and or we would go ahead and put the stuff in change history tables, i.e., we as the database developer, yes, again, people might scoff at the idea, but that's what we were considered at the time. We would go ahead and create separate tables, which the whole purpose is that anytime we did an insert or update or delete or whatever, we would run a trigger. The trigger would then basically copy whatever data we were going to modify into a change history table. So that way the summary table stayed the same. No, sorry, had the update or the delete or the insert, but then the new information, any changes would then show up in the change history table. Okay. And so this itself, of course, was a very tedious process on its own. So that's actually how you did data versioning. And then how about if you want to track like additional processes specific to your environment? Like what version of SQL were you working with? What version of the .NET C++ con object code? Yes, again, I'm not trying to make you scared about that concept, but to go ahead and do that. Okay, you would actually typically have metadata or master data management to track all of these things. And by the way, don't worry, I'm about to switch back to software engineering practices. I wanted to call out some of the issues with the state first. Okay, so all right, let's see what else we want to discuss. All right, but then how about if we wanted to allow multiple people to read and write your data? Well, this is one of the great things about databases, and that's why databases dominated for the longest time on how we managed our data, right? Multiple clients were able to concurrently read and write to data. That's something you couldn't do with an Excel spreadsheet, okay? In production, like maybe we'll only be able to use a single service account, but there's security. So that became its own massive set of guidance that you'd have to follow. But at least, yeah, you can go ahead and do that. But the key aspect here, the key thing that you want to call out, and the whole reason why databases became so powerful when it came to business data operations is the context of CRUD operations, create, replace, update, delete operations that are protected using ACID protections, i.e., I'm going to talk about that a little bit in a second, but the idea is that the data was protected right from the get-go. All right. So in other words, either the delete happened or it did not. Or in other words, if it happened, that means we're sure that we had transactional protection to say, yes, the delete happened, the data has been removed. If there's an error in any part of the process, the entire thing's rolled back. So that way the delete either happened or it didn't happen. This allowed you to go ahead and reprocess, like retry logic and rerun the delete all over again, because you don't have to worry about the fact that you were running duplicate deletes and by accident deleting something else. The problem typically was that if you wanted to track everything that happened, this typically required separate logging and authentication systems. But that ACID protection, ACID transactional protection, that was the key thing that made databases so important to how businesses ran. Okay, it's so important that in fact things like rolling back to previous versions weren't actually considered first-class citizens. So, for example, if I made a mistake to the database, I'd actually have to restore the database backup that I saved and tape backup or somewhere else. This is a very time-consuming process, and yes, very susceptible to human error. And maybe you had developed a system so you actually did change tracking tables. That was great, but those weren't always implemented and was very resource intensive. And the key crux here is that often the rollback process actually just wasn't available. Okay. And then if I wanted to go ahead and say, hey, can you explain to me why you made that change to the data? Like, why did you update this? Why did you delete that? Well, there's actually a burgeoning there was at least a burgeoning metadata master data management industry to try to help you with that. But like, there's no, for example, Git comments for data versioning. Even small data isn't very well tracked. Like, for example, that's why SharePoint's around, because it allowed you to track the changes to your different list. And the reality is the data for SharePoint wasn't terribly big. And even if you didn't care about that, when it comes to like talking about streaming and big data, this concept was basically non-existent for all intents and purposes. And so what it came down to is this: because you were building everything a la a monolithic architecture, i.e., you're dependent on the database, your software engineering practices weren't even close to what you see today. Okay. In fact, you'll hear me talk about this a little bit later, but the reality is that for the longest time, the data engineer and the software engineer actually were two different things. They actually weren't the same thing, right? Because the data engineer was actually just it was an application engineer applying SQL scripts. And the key thing was basically this: it was really complex to maintain the code, let alone maintain the data versions. Because it's a monolithic architecture, deployment became a massive bottleneck, right? So for example, I want to change a table to add additional column. A lot of changes, even adding columns to database tables, resulted in taking the system offline or at least slowing the performance down. Even if you could do it as an online change, you had to be concerned what was the impact of the downstream systems. For example, people would often run queries that would just simply select star from a table. So if you added a new column to the table, it might screw up the downstream systems because they were expecting 7 columns and now there's 8, right? Again, horrible best practices, don't get me wrong. But the reality is that's exactly how these systems were designed. So it made for development cycles that were really, really slow. And because they're always afraid that you're going to break some downstream system and they had no visibility of those downstream systems, there was a real fear to change, right? And so typically what ended up happening is if any of the database systems that were successful or monolithic architecture that were successful, there was a single person, one person whose job was to look at the whole overall system, see where every single store procedure was operating, see where what every schema change was happening, what was happening upstream, what was happening downstream, to see the whole vision of the entire thing. Okay. If it's a small system, that is plausible. But as systems become more and more complex, this was completely untenable. Right. So, and because of the fact that this was already happening before even the realm of big data, basically there was a lack of ownership, right? So because even if the architect knew how to see the end-to-end upstream system and every downstream system, the reality was that they actually didn't maintain the systems themselves. They would be the ones to guide the database developers or the application developers to make the changes that needed to happen. So they weren't actually owning everything. So it was actually the owners were downstream or upstream for that matter. And then they themselves usually had different bosses that had different priorities anyways. And so, and then finally, I did want to call just to overharp on this point. Basically, we had one size. There was a database. So it just didn't, you can't follow that flow of one size fits all. It doesn't, right? So that's where the relational database was, because it was the context is that we had consistency and availability. We always had these transactional protections, but as time progresses, and we're going to talk about this in a second, did you really need all those things? Especially for this last case of the fact that it's really hard to scale out, right? So I have a section actually in the course where I talk about sharding databases and things of that nature. But the reality is that even if you were an expert on sharding your databases, and so you have like hundreds or thousands of MySQL or SQL Server instances, the skill level to maintain these things was immense and the benefits rapidly reduced. Okay. And so in the aughts, roughly, we made the shift to microservices. And so you'll notice that, for example, in the previous slide, I said the source was from, microservices on AWS, okay? And basically, that's the key tenet here, that this perfect storm of cloud, big data and microservices end up creating a pretty cool thing where basically a lot of us were following the 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 push for development a la AWS and Netflix. So you'll actually see attributions all throughout these slides about exactly that. And so when we talk about microservices, there's also a lot of related concepts like SOA, service-oriented architectures, API first, agile, continuous delivery, DevOps. I'm not going to dive into each and every one of those, but the context is they all sort of follow the same flow from the standpoint that we don't want monolithic architectures anymore, right? In order for us to scale, we actually have to go into microservices. And here's a key thing that I like talking about microservices, which is basically these characteristics. It's very decentralized. So you don't have this one gigantic team of 50 people trying to develop the code, right? Typically it's I think I mentioned this in the slides ahead, it's a 2 pizza box team, right? You're talking 5 to 10 people that are actually working together to deliver the code base, right? But they're also delivering it end to end. So they don't just deliver it, throw the code over to the tester runs it, and then they throw it over to the operations and the operations people go ahead and deploy it. They actually have to make sure they understand how everything works. This is actually really crucial, by the way. It's not just about owning the responsibility of the developer to actually know what happens when they have to deploy something. The other crucial thing that's happening here actually is that they actually have to understand what are the characteristics of the system they're running on, right? Is, for example, the disk that you're working with ephemeral? Is the network has high latency or low latency, right? They actually have to be aware of this fact. They can't just simply say, okay, operations is going to automatically give me consistent latency, consistent disk speed. It doesn't happen that way anymore, okay? It allows for polyglot, i.e. whatever language, whatever framework, each team can independently do their own thing without any problem. Because they can do their own thing without any problem, they own it end to end. So if they decide they want to write in Clojure, go for it, write it in Clojure, okay? They want to write it in Scala, write it in Scala. That's up to them. They're going to maintain this, okay? So that's what you get with independence. And because of that, it's a black box design, all right? So in other words, if I need to use your microservice, there basically is only a contract here, right? I'm going to tell you, you're going to tell me you're expecting this input of this JSON file, and you're only willing to receive 1 JSON file per second or something like that, okay? Whatever that contract says, right? Or SLA for that matter says. And then the microservice itself, it says, okay, got it. Well, then in return, I will give you these recommendations in this JSON schema at a rate of 1,000 JSON files per second or whatever it is. And so whether I designed that microservice where I receive a JSON and deliver JSON up to 1,000 JSONs back to you, you don't care if I wrote this in Clojure. You don't care if I wrote this with a pigeon carrier, right? You don't care how I designed it. You just care that I've delivered that to you. That's all you care about, which makes sense because then that allows that one team to do that one thing well. So in other words, the team that actually is receiving the 1 JSON and giving back up to 1,000 JSONs recommendations per second, whether they decide to use carrier pigeon or or sending or just writing this in Clojure or in Fortran 77, you honestly don't care. You just care that you're going to be returned that JSON document or documents and at the consistent rate that you said your contract said it would, right? And so that way, myself as a developer, when I'm building my recommendation service or I'm building my product catalog service for my e-commerce site, for sake of argument, I don't have to care now. I just know that they're going to give me 1,000 JSONs per second, provided I give them this input. So then I can focus on the other thing that I need to go do. All right. And so this allows your individual teams to do that one thing really, really well. Right. And so that was the change. And so for many who, for example, are going to college right now, they're going to say, well, duh, this is exactly how you're supposed to do it. And that's right. That's right. That I agree. But at the time when we were making that transition, this was not very obvious to us at all. We were used to this idea that databases were the way to go. And in fact, many businesses that are running right now still think that way because that's the legacy systems that they're still currently on, right? So they don't inherently understand these characteristics and the benefits of it, and also don't inherently understand some of the drawbacks, which we're about to talk about. Okay. And so, but let me talk about the benefits first. So this is again, from the microservices on AWS. This is a view of Amazon.com by its microservices. Okay. And so there's something like 30,000 little different, at the time that this is, I think, 2000 from a slide deck from 2016. This is like 30,000 different API endpoints that make up Amazon.com. Right. So back to my point about, like, in the past, when I had a database monolithic architect, I could have the central or one key database architect or software architect that could understand the whole system end to end. Well, what's the likelihood of anybody understanding 30,000 endpoints end to end? And the answer, of course, is it's not going to happen. And so that's what microservices was able to do. So in other words, I don't have to understand the entire thing. I just have to understand what's upstream of me, directly upstream of me, and directly downstream of me. And technically, I don't even have to understand downstream of me because I've already provided the contract. It's just that typically you're going to work with the developers downstream of you because that's the service you're providing. Okay. But that's it. I don't have to understand all this entire graph of all the different interconnections. They basically are able to, this Amazon.com is a summation of all of those connections. All right. All right, there we go. And so, like I said, it all started with this concept of 2 pizza box teams. And the real benefit, like I said, it's because you're only talking about 5 to 8 people. Oh, sorry, 5 to 8 to 10 people, depending on how you design it, with 2 pizza box teams. The whole point is team autonomy and speed. You let the team decide. So if this team is, let's just say, of 8 people, is primarily great at writing everything in Python, then the fact is they'll probably write their APIs in Python as opposed to being forced to write the stuff in C#. That's great. So they've got the autonomy, and because they know the team's strengths, they can have better code quality. That's awesome. So they can go significantly faster. But the key facet here of this 2 pizza box teams idea really is better, easier, smoother communication. That's what it boils down to. In fact, this a lot of people attributed this concept to Amazon. And while Amazon certainly made it popular, this idea of 2 pizza box teams, this is actually a standard, well understood concept within the military. Okay, I actually am part of the King County, Washington here, search and rescue operations, and so that's exactly how we're trained right from the get-go. Right, we're trained with the idea that if you go in teams, we're going teams from somewhere between 5 to 10, because whoever's in charge, that person in command, they can only effectively communicate with 5 to 10 people, and that's it. And so you always make up your teams in that size. Right now, obviously, sometimes 4 is better, sometimes 11 is better. This is a general rule of thumb, but the context here is nevertheless the same. It's about ensuring smooth communication. Okay, and so, I'm only doing a brief version of this microservices approach. But for example, if I was building this e-commerce site, right, I have, instead of actually trying to build everything, I have individual teams that, like, for example, I'm going to build a catalog service versus a display ad service versus an alerting service versus a messaging service versus a recommendation service, right? The display ad service decides that it wants to use Cloud Object Stores. The catalog service decides it wants to use a document store service. The alerting and messaging services want to use a message store service. That's fine. But the key thing here is that there's a separation of the business logic, which is basically these recommendation, messaging, alert, whatever services, from the data. The data could be in a callable object store. It could be in a document store. It could be in a message store. It doesn't matter. It's up to the team to decide. If they want to go ahead and change what object store they're using, the data store they're using, provided they still can meet the SLAs that they've already said that they're going to meet, it doesn't really matter. So in other words, if one day I'm using Cassandra and the next day I'm deciding to use the file store, like, S3, Well, provided you can still give me 1,000 JSON files per second for my recommendation service, I really don't care what you're using. And that's more or less the point. There's that separation of business logic from data. Okay. And so this is actually the point, right? So we can change the service in the stores for the data provided. They have the same entry points. Okay. So now that I'm saying all that, what is the state of your data now? So you can keep track of which versions. Yeah, so you can employ better software rigor, okay, around this. You can, but the problem is that you might end up having with many different stores because different teams are going to say, well, I prefer one thing versus another thing. And since they have the independence to do it, they might choose multiple different storage mechanisms. And you'll quickly see where this might go awry. All right. It is because in terms of keeping track of your data, the state of your data, like it can't, it's each has to be maintained and operated pretty much pseudo independently. And the reason I say pseudo independently is because for your specific service, yeah, you can go ahead and maintain state for your service. But how about if you have to maintain service state across all the services? This is where that becomes almost like an anti-pattern when it comes to microservices, because that means now you have to have this global view. Okay. I think I call this out later on, but how that often is resolved, especially in larger environments, is that there'll be a central team that builds a log service, and then all the services will always use the same log service, so everything's recorded in the same way. And then and if there's a relationship between one microservice to the other, they'll pass a correlation ID of some type. So that way you can track what happened to, like, for example, the deletion of this particular data across the 5 different services. Okay. So this, of course, becomes a little bit more complicated to say, to put it lightly. Okay. And it's very well designed for that scenario. We're going to talk about the big data landscape in a second. Okay. Sorry. There we go. Perfect. It's right here. Okay. And so that's more or less the problem that I was referring to in terms of, if you have independent teams, maybe they'll choose which store or which database or platform that they want to do. This is actually from Big Data Landscape 2016 version 3.0. Any operations team is going to just tell you, yeah, you're not allowed installing whatever you want here. You're going to be limited to X, Y, and Z in terms of like what stores you're allowed having. And the reality is, yeah, like all these systems appeared because they were really well targeted for their specific environment or their specific set of problems. But there was no attempt to say, well, hey, some of us are actually solving very similar problems. Maybe we should coalesce together, which is you're starting to see that happen right now. Okay. So let's continue on to state of your data. I'm going to finish this part in a couple minutes so that way we can get to the end point here, which is allowing multiple people to read and write your data, which is great. It's really well designed for that. But, and for example, if I talk about the CAP theorem a little bit about consistency, availability, and partition tolerance, that's great in terms of the fact that I can choose whether I prioritize consistency over availability or availability over partition tolerance or whatever two you have. But as you'll note, basically you only get to choose 2 out of 3. Any system basically is only able to do a good job with 2 of the 3 of the CAP theorem, and they'll build systems to work around the third one, right? And so you can definitely go into that idea of choosing the right tool for the right problem. But now it's really hard because if you are one team that has to maintain multiple microservices and now you have to maintain multiple stores, I hate to be the team that has to maintain Mongo and HBase and Cassandra and Redis cache all at the same time, right? There's only 11 of you or 10 of you. That's going to be really difficult. Rolling back is almost impossible, by the way. Okay. You can do it insofar that, like maybe there's a log that tracks everything, but don't forget the impact of microservices is that you got to track everything, right? You have to go back to every single microservice, and that's difficult. So you how to track that state, it can be virtually impossible to do, actually. And forget about explaining and commenting why the changes. I mean, you definitely have from a software perspective of saying, let's go ahead and explain why to me the changes of code, but I didn't do a good job explaining what I do with my data. And so what it boils down to basically is that if you go ahead and look at all these different systems, it becomes that much rapidly, like, sure, monolithic architectures has its problems, but it had ACID transactions at least to protect the data. Microservices solved a whole bunch of other problems in terms of scale and efficiencies, but it actually didn't solve much on the data side. Okay, it solved the ability to be concurrent, but it made a bunch of assumptions on what you did with your data. Okay. And so when I talk about Netflix, the principles of chaos engineering, I'm actually talking about the an actual blog post as opposed to some show on Netflix. Okay. And this is back at the time, the whole reason we cared about what Netflix did and we kept on reading what Netflix was doing was basically the dream of scaling up linearly. Like, as the fact was that we had a database, all we could do is add more disks, more CPU, more memory. We would hope the heck this thing could scale up, but the reality is that never happened, right? You always would hit, the laws of physics to prevent you from doing that. Well, in the case of like Netflix saying, let's just go use Cassandra, they were able to now scale, add more nodes. I can go ahead and scale up faster, which is the dream that we love. Okay. But in order to do that, they had to actually understand that, as opposed to the monolithic design where basically everything had to be perfect end to end, we actually had to start switching our mentality, which is that we actually had to create failure. We actually had to understand the fact that things are going to fail. And so this is basically the key principles of chaos engineering, right? And so the quick summary here basically is this: you build a hypothesis around what you think is steady state, and then you measure. And I know that seems obvious to you, but when we built database systems, we actually didn't do that. When we built database systems, monolithic architectures, we often did not vary the real world events. We just assumed everything would come, everything perfectly. No, real world is chaotic. You actually had to run experiments in production. Okay. So because you actually had to see what happened, and you need to automate those experiments and run continuously, which we actually weren't doing a very good job of. All right. And that's more or less the call out. So what we did in reality is that we would try to do that, right? They all tried to be like Netflix. So you had like small companies, big companies that had built legacy software systems that were used to building software packaging, and they completely forgot how to. They think that they could build a hybrid of this, where they said, okay, well, I used to do the waterfall software development lifecycle. I can go ahead and go agile tomorrow. So because they'll just build hybrid systems. But then, of course, what ended up happening is that you just extended existing monolithic architectures. That's all you did. So you actually never really, really benefited from any of this. Okay, that was ultimately what ended up happening from a software engineering perspective, because the developers never learned what that shift in thinking was. They never learned that they actually had to design failure right from the start, right? And so when it came to data, when I switched back to the microservices side of the thinking, it's like, well, yeah, we're always talking about the three V's: the volume, velocity, and variety, right? And the whole context of big data is that you typically had to handle at least two of the big three V's, which is that I had massive amount of volume, massive amount of velocity, and or a lot of variety. And because I had all three of these, two or three of these things happen at the same time, this is what was big data, because it was hard for any one system to solve that problem. What was lost, going back to databases, was that concept of veracity, the fourth V, or data reliability, which is, okay, well, wait, how do I make sure whatever data that I write to any system, like to a cloud object store, actually is exactly what I say it is, right? Because when you save to a cloud object store, if there's an error in, like, for example, a Spark job, and it rolls back, it leaves files. It can't roll those back. So what do? Right? So do you overrun them? How do you clarify that? Do you build a script to automatically delete? Right? This gets worse and worse and worse. But when you're dealing with larger amounts of data and they're going faster, because the reality is you can't track that stuff. Right? That's just, they're going to leave potentially corrupt your data, but they're going to leave orphans behind, which is really bad. And so that veracity goes back to require us to talk about your data. You actually need data reliability, and that requires ACID. And so the context is that, now that I'm trying to sort of summarize everything back together, is that we started with databases and ACID was awesome, right? And I'm not talking about the drug, I'm talking about transactions. Okay. So that's great. But when we shifted over to big data and microservices and cloud, which was amazing, and it's the right way to doing it, absolutely, we lost this concept. We lost this idea that we needed atomicity, consistency, isolation, durability to protect the data. And so now, slowly and steadily, that's exactly what's happening in software engineering with data and AI. We're actually slowly going back and recognizing there are some key facets of monolithic architectures that are actually extremely important, even in the realm of big data, even in the realm of cloud services, even in the realm of microservices, that we actually need to go ahead and find a way to ensure our data is reliable. All right. So how do you bring veracity or reliability to all of this? Okay. Right. So this is where I'm going to sort of finish off on terms of the software engineering thing. In the past, 60 to 85% of our data warehousing projects had failed. Okay. And these are, because I'm a little short for time, I'm going to skip through these slides. But the context is that, hey, Monolithic had these problems like using waterfall methods of microservices. We said, hey, we're going to do agile development. We adapted a lot faster with microservices, cloud, big data, that monolithic architectures required 8 months of functional specification reviews, right? This was great. So now, because of microservices, we solved everything, right? Well, so what was the result? Well, all we did was change from 60 to 85% of data warehousing projects failed to 60 to 85% of our data projects failed. That's all we did. We actually didn't change anything, all right? But the key thing is that they failed for very different reasons, right? With the case of monoliths, they weren't not agile enough, and frankly, they're, just like we said, monolithic architectures. When it comes to microservices, there are too many options. Right. So you have your 10-person team that now needs to maintain 4 different data stores. That's completely untenable. Right. And there was also the fact that you lack data reliability or veracity. And so because you lack that protection of your data, then all of a sudden, boom, you lose your data or you've corrupted your data. All right. And so then we actually went ahead and even jumped into the cloud, and that made things even worse. Okay. All right. And so let me just talk a little bit about like how Amazon got involved with all this, right? Basically, once we went to the cloud, basically Amazon had to change that monolith architecture into the microservice, because since Amazon was growing really fast, the key tenet was that IT wasn't keeping up. All right. And so the tenets actually can be summarized by the one Netflix blog piece, which I'm just going to do a quick summary of, which is Dorothy, we're not in Kansas anymore. Okay. A la 5 lessons we've learned using AWS. And the context is that Dorothy, we're not in Kansas anymore is simply saying, okay, everything you learned in the past is no longer applicable, but you have to change your way of thinking. So again, monolith architecture, switch over to microservices. These are 2 very different modes of thinking. If you, as a student of these courses here at Berkeley, you could probably call yourself a microservices style thinking. That's great. But it's more than possible any of the people you work with or work for who are in leadership positions, they're still thinking in monoliths. So you're going to have to make sure you're going to be able to connect the 2 and understand the software engineering practices of the SQL developer and what who uses writing SQL scripts versus writing in Scala, Python, JVM, C++, using GitHub, using agile development. These are very different ways of thinking. A key facet of co-tenancy is hard, especially in this perspective, is that these systems are not reliable. So you have to figure out what happens if a system gets saturated. And you build into your code, into your service, how to respond to that, right? And so that really leads to number 3, which is the best way to avoid failure is to fail constantly. Like, how did Netflix go ahead and make sure they could always keep up and running a la Chaos Monkey? Well, in the early days of Netflix, what they did was they literally would purposely kill your connection to watching what your show / movie. And because they killed the connection, the idea is that the client on your computer or whatever was able to reconnect to Netflix anyways. And so you should have still had smooth sailing and you should not have seen anything else, right? That's like what we mean by testing in production, but it requires a lot of thinking. So you plan for that failure. You have to play at real scale. Typically, especially in the past, and people still do this today, it's like, oh, I'll just take a sample of data. That's great. when you're doing initial development, I'm perfectly fine when you're taking a sample, but do understand when you have production levels, which are where you're doing tens of thousands of transactions per second, you sure as heck have a design to actually handle that, and you've already tested for that. And a key thing is you got to commit yourself. So for the person who's the monolith architect and has a team that's used to developing software that way, they have to commit themselves to actually learning microservices. They have to help their development teams learn how to do that stuff. For people who are already on the microservices, they have to commit themselves to understanding some of the facets like ACID transactions for data reliability, so they actually can protect the data, right? And so it's about basically saying that, being able to go ahead and use the right tool for the right job. And I did want to finally end with one key point about culture. I know that sounds weird to be talking about that when I talk about software engineering practices, but the thing is that what's implied with everything I'm saying is that monolithic architecture, how you design, how you build, and how you architect, how you develop, and microservices actually are two very different ways of thinking, i.e. two different cultures. And so there's actually a link here. I'm going to send you guys these slides, by the way. So you can click on it. It's actually a 200-page blank white PowerPoint deck. This is normally the worst thing for me to be suggesting to anybody to read, but it actually ends up being one of the most interesting reads because it was talking about the freedom and responsibility that Netflix culture has created. So the key facet when it comes to at least data is that not all people who are like DBAs, they want to make that shift to microservices. So yeah, you're going to train your team and you want to be patient so they can make that transition. But it's a major change in their career paths, and they may not want to make that change. So some are going to thrive in this new environment, and some will not. Okay, and that's actually okay, but provided you remember this key facet, which is not all culture. The culture is not going to satisfy everyone, which is exactly the point. The cultures are there to maintain, find, keep, reward the people who belong in that group, right? It's a good source right there. And so when you build your team, when you're part of a team, finding that culture, if you're the only person who's building microservices and you're surrounded by monolithic architects, if you try to introduce, Maven, GitHub running in Scala code, those practices are almost the antithesis of what a database developer is going to want. Now, if they're willing to learn, that's one thing. But if they're not willing to learn, that's your problem. Okay. And so this is one of those key facets that is often forgotten about. It's not just about the tech here. Like when you talk about software engineering practices, it's about the team makeup. It's about the people you work with, the people who you consider leadership. And you have to make sure you understand what those things are, because that aspect, i.e. the culture, is crucial in order for you and your team to succeed. Okay. And so this is it for the slide session. So then we can switch to questions. Key themes: use the right tool. Use the right tool for the job. Microservices and learnings. Microservices and learnings from monolithic architecture, as opposed to the two competing. A facet that I didn't describe as much as I should have, but it's basically over time, because we're talking about ACID transactions and data reliability that we learn from monolith architecture versus the benefits of microservices. What you're seeing today is that convergence of data engineering and software engineering. It's actually happening in real time right now, which is pretty amazing. And the final aspect, culture is important. Cool. Excellent. And that's it for today.
Thank you so much, Denny. I really love that, a talk that's focusing on data engineering and technology ends with a discussion about culture and how, it really brings home the point that most technical problems are actually socio-technical problems.
Exactly.
Yeah, but we do want to spend our last few minutes here addressing questions that folks have. So if you do have a question, you can post it in the Q&A panel. You can raise your hand and we can enable your mic to ask your question. We do have one question already from Kiran Prabhu. Kiran asks, allowing multiple people to write your data can be risky because if something goes wrong, it will be very difficult to roll back the changes since it's going to be time consuming depending upon the size of the data. And this in turn will affect the performance of the application. So how do you handle this?
So that's the key thing. You've brought up a really good point when it comes to, for example, a database can potentially solve that problem because you can ensure the ACID transactions are there so you can go ahead and, ensure that nobody's making mistakes. But in your case, it's not even so much they're making mistakes. It's that you actually want to allow multiple people to write at the same time, and you want to maintain previous versions of the data. So because of that, what you actually need is a system that actually does exactly that. So for example, like now I'm harping Databricks a little bit, but as you'll notice, I was actually trying my best not to be very specific about Databricks here. But for example, we have a technology called Delta Lake, and the whole purpose of it is that you can make insertions and updates to it, but it's MVCC, right? In other words, it keeps multi-version concurrency control. So the idea is that each person who does a transaction, we keep that version of data. So it's possible to roll back, right? So that's an example of like how we're building new technologies to address that, precisely because of these new problems. And that's what I meant by like, you're starting to see that convergence of data engineering and software engineering, because and to call out my own competitors, like that's why you see Delta Lake. That's why you see Iceberg from Netflix. That's why you see Hootie from Uber. We all basically came to the exact same conclusion at the exact same time. We're realizing, oh crap, we forgot a lot of stuff, right? And so Delta Lake literally was born not so much because we had this awesome like thinking to ourselves, we know exactly what's going on. No, we had a bunch of customers screaming at us, going, dude, I had a bunch of people write stuff and I need to roll back. Crap, how do we do that? So that's how we solved it. Okay.
Great. Thanks, Denny. Another question from Max Zip. Max wants to know if you could talk more about convergence of data engineering and software engineering, and follow up, are there new technologies or new development regimes or what else?
Sure. So when I say by the convergence of data engineering, software engineering, actually, I'm going to use a little story to provide that context. Okay. So in fact, it's actually part of the MOOC that I have. So there's a buddy of mine, Tasso Larissis, cool guy. We worked together about 6 years ago. I was the senior director of data science engineering. Wow, that's one heck of a title. At SAP Concur, he was the senior development lead for the expense product. Why am I bringing this up? Because he was a Java head. Like we're talking hardcore software developer Java head. Okay. It's not. I'm not trying to insult his data skills. He definitely knows SQL and knows his data and knows how to work databases. But he's a Java head. Okay. Me now he's a Clojure head, by the way. But at least before he was a Java head. Okay. Myself, I was definitely more of a SQL head. Now it doesn't mean I can't write the code. And don't worry, I'm not telling C++. C#.net. No, I mean actual like Scala, Python, C++ code for that matter too. So like real software engineering. But the reality is also I was more of a data head, so I was wrapped my head often around SQL. So because of that, we were talking two very different languages. Now, the whole premise of me telling you the story is that 6 years later, when I interviewed him, what are we talking about? We're talking about microservices. We're talking about REST API. We're talking about endpoints. We don't care about the language anymore. He might be writing Clojure. I might be writing Python. It doesn't really matter. We've got a REST endpoint that he can talk to and I can talk to. We don't care what language you're using. So even though now he came from a very software engineering centric background, I came from a very data engineering background, didn't matter. We're converging on the exact same concepts. So that's what I mean by this convergence. This idea that even people who are hardcore one side or the other, we end up doing the exact same thing. We're talking the same language all the time now. All right. And so in terms of the second point about like, like, are there softwares? Again, Delta Lake is one example of that, right? It's exactly that concept, which is to say like, okay, we were able to do the big data microservices thing really well. Awesome stuff. Perfect. Except guess what? People were making mistakes. There were errors. We're leaving, if a Spark task failed due to some insane ask of 1 billion iterations. Okay, well then how do you roll back? You don't, right? So instead, we actually built a mechanism to protect the data. We actually, literally, we leveraged our learnings from databases. We built a transaction log. That transaction log protected the data. Now that the data is protected, if the task failed, yeah, maybe we left orphan files physically, but the transaction log doesn't record it. Since the transaction log doesn't record it, doesn't matter. Data doesn't exist. You're good to go, right? And so these are small examples of what I mean by that convergence of software and data engineering, where we're recognizing the patterns from the past are still very much applicable today. And just that final call out, many of the learnings or how we design the cloud literally came from the mainframe era. Okay, I'm old enough to actually talk about mainframe, okay, which is now I'm really aging myself, but that's the context. A lot of our learnings, yeah, the same mainframe, i.e., I'm doing Fortran punch cards. Yeah, same one. Those concepts actually are applicable to how we design the cloud today.
Great. There's one question here from an anonymous attendee.
Sure.
I'm not really sure if you'd be able to answer this, but we'll give it a shot.
Sure.
And I can chime in as well. Are there classes at Berkeley or Denny anywhere that would best prepare students for the convergence of data engineering and software engineering?
Okay, I wouldn't be able to tell you what classes in Berkeley specifically, obviously, but I would be able to tell you this. There's two things. One is a shameless plug for me, but one is actually obviously for Berkeley. Okay, so let me start with Berkeley first. Look, Berkeley is a damn amazing comp sci school. Okay, let's be very clear. Okay, like you even like I won't say you're better than UW just because I'm from Seattle, but seriously, you guys are amazing. Okay, so the founders of Databricks are from Berkeley, for crying out loud. So we're talking like you're an amazing school. So if you can't learn this stuff from Berkeley, I have no idea where you're going to learn it from, really. Okay, seriously, I can't I can't even explain that concept. Okay, so the key thing is that you do want to make sure that in addition to learning everything you want to learn about microservices as a software engineer, you do actually want to understand the internals of a database. Even if you don't use it, like you actually want to understand concepts like relational algebra. You do actually understand what B tree, what's an AST, right? Because if you even look at Spark right now, what literally, when I look at the catalyst optimizer for Spark, right? Everybody's talking about RDDs or Scala or whatever else. What's the catalyst optimizer of Spark? Literally, it's a logical and physical optimizer. Where did that concept come from? From databases. Right. So even when we built Spark, when we started creating Spark SQL and all these other things, we literally were borrowing from the database concept because we realized there were actually a lot of cool things. So if you're going to want to see that convergence, that's how you do it. You actually want to learn, even if you don't intend to ever use a database again, you want to learn the internals of a database. Okay. And the other thing, now this shameless plug for me, well, I did mention there's a Coursera MOOC coming out at the end of February, early March, called Bring Software Engineering Practices to Data and AI. That's exactly what I'm doing. I'm actually going into much deeper details on the stuff. And what I'm doing is I'm actually not just talking about from my perspective. I'm also interviewing other people from the field. Okay, from like I've got an EVP from Tableau. I've got a co-founder. No, not co-founder. Actually, I've got a co-founder too, but I've also got a founder of a startup. So I've got a lot of people from different facets of life, whether it's an architect to like people who run the business and hiring teams. We all actually talk more or less the same language, even though we have very different backgrounds. And so I would highly suggest these two modes of learning.
Thank you, Danny. And I will say within MIDS, assuming that the person is related or a student of the MIDS program, I would say your best bet would be to talk to folks who teach in 205, our intro data engineering class, as well as the team who teaches in 251, our deep learning at the cloud and at the edge class, because I think there's a lot of experience there in terms of software engineering brought to more infrastructure problems and cases. So that's probably another place you could investigate that a bit further. But Denny, I'll check out your upcoming MOOC as well. That sounds super interesting. Cool. I want to say thank you so much again, Denny, for sharing all your thoughts, your insight, your experience with us. Great presentation. Thanks so much. I also want to thank Databricks for hosting this lecture series. Look out for our next talk in the series, which is planned for February 10th. And thanks, everybody. Thanks to all of you for joining us tonight. The recording of the presentation is going to be posted on the event page of the iSchool site probably in about 10 days or so. So thanks, everybody. Take care.